our second review. In terms of what we're going to be doing today, I will be focusing on, of course, reviewing the material with you guys, but also at the same time, giving you guys a bunch of examples to work on. Cool. So for those of you who have been to Learning Den, it's not going to be as much just like regurgitation of material. I'm not going to be spending as much time on that, but rather we're going to be looking more at examples of problems that you might be encountering on your exams. Cool. In terms of technology, I haven't had any issues today, but of course, when I work with you guys, it's always different. I might need to turn off my camera if that makes my quality better. So if I do that, then you know why. Okay, so let's get the show on the road. All right, so yeah, we're just gonna basically start by looking at reactions and their mechanisms. I'm gonna be dividing them based off of the type of additions that you guys will be seeing. So whether they're syn and anti-addition, just anti-addition, or just syn addition. So the first type of mechanism that we'll be looking at will be our carbocation mechanisms, which you guys all should know by now that they undergo both syn and anti-addition. And that's just because of the fact that you have a planar intermediate, right? That carbocation is sp2, and you guys know that the hybridization of an sp2, or the geometry of an sp2 atom, is going to be trigonoplanar. In terms of double bond reactivity, carbocation mechanisms experience rather different double bond reactivity compared to non-carbocation mechanisms. And we're going to be talking about that later on. Finally, or not finally, the regiochemistry is based off of where the most stable carbocation forms. Again, largely governed based off of Markovnikov's rule. And then when you're looking at the number of stereoisomers that form in a given reaction, your stereoisomers is going to be given by 2 to the n, where n is equal to the number of new stereocenters. Now, with that word stereocenters, I am including the fact that you can potentially get cis and trans isomers about a ring. And we're going to go ahead and talk about that again later on when we work on more examples. So in terms of why syn and anti-addition is observed, remember that we have, again, that carbocation intermediate there that we have there, and then we have some sort of generic nucleophile. So the nucleophile, you know that there's nothing really hindering it. Of course, the hydrogen does not hinder things that much. So the nice thing is that here, the nucleophile can easily add in from the top or from the bottom without any possible hindrance. Cool. So because of that, we do observe both syn and anti-addition with these reactions. Okay. So in order to understand these types of reaction mechanisms, it's good to look at carbocation stability. Okay. So this is, just a rather general list of where you the types of carbocations you can get along with their stabilities. You see that in terms of your carbocations, the more stable one would actually be the tertiary allylic carbocation, right? Remember that there is a difference between the word allylic and the word alkyl, and of course vinyl as well. Cool. When we refer to alkyl carbocations cannot resonate. Okay, they cannot delocalize their electrons by resonance. They only delocalize their electrons by something. By what?
Hyperconjugation.
Hyperconjugation, very good, right? And remember, hyperconjugation is just the principle of being able to donate electron density into the NTP orbital that houses the carbocation from the sigma bonds that are neighboring, right? It's pretty much the alignment of the sigma bonds with the FTP orbital. When we refer to an allyl carbocations can be delocalized by resonance. Okay, so you see that with all these allyl carbocations, I have a potential resonance structure, right? I'm not going to draw it out for you guys, but you guys know how to draw resonance structures by now. So go ahead and test them out, and you guys could see that because of conjugation, these carbocations will be delocalizable. Cool. And we get to some of our more unstable carbocations, such as our alkyl. Primary alkyl, it's a carbocation that's on a carbon that's only bound to one other carbon. You only have hyperconjugation on one side. You're really rarely ever going to see that. And the carbocation that I've drawn here is probably the only case of a primary alkyl carbocation that you will ever see that's not stabilized by something else. Methyl carbocations are also very, very unstable as well. You need lots and lots of energy to form those. Another one is vinyl carbocations, which you see that I've drawn in blue there on the right. You guys know that vinyl carbocations are very highly unstable. What are two reasons that these vinyl carbocations are highly unstable? Someone give me one and someone else can give me the other.
There's a positive charge on a electronegative carbon.
Very good, right. So we know that that carbon there is more electronegative than the other carbons that I've drawn on the page because that carbon is sp hybridized, right? You could tell it's sp because of the fact that it's linear. Cool. Remember that sp has the greatest s character compared to something that's sp2 or sp3, and having a positive charge on something that prefers a negative charge is not preferable. Cool. What's another reason for why this vinyl carbocation is unstable?
There's no
Hyperconjugation.
Right, you have very minimal to little or to no hyperconjugation, at least on one side, right? In order for hyperconjugation to occur, the sigma bonds have to be aligning essentially parallel to the MTP orbital. Okay, if I were to actually go and then draw a molecular orbital depiction of how this would look like. Okay, here's my MTP orbital that houses my carbocation. Remember that has to be in the same plane as the hydrogen sigma bonds. You observe that they're not exactly parallel, right? The carbon hydrogen bonds are kind of like tilted that way. So pretty much you get about the same amount of hyperconjugation as you would for not a primary alkyl carbocation. Okay, of course their stabilities are not exactly the same. They vary depending on the molecule, but you should just be able to differentiate what is stable and what is unstable. Cool. We want to focus on understanding which ones are the most stable. Okay, so, and don't get into the nitty gritty of determining, oh, what's more stable, a methyl or a vinyl or a primary. Okay, just know those are all relatively unstable. Cool. Of course, you know methyl is less stable than alkyl, but you know that those aren't going to be the ones that you're going to be seeing in reactions. Cool. So make sure that you're taking all these factors into account. Cool. So again, these all build on concepts that you guys have learned previously. So we're going to go and then quickly go over the mechanisms. You guys may remember that in the past I've gone over the mechanisms with the forest perspective, but I already showed you guys the forest perspective in that little example that I gave earlier. Remember, except the fact that you're going to have syn and anti-addition because of that planar intermediate. So if you guys remember, a mechanism like hydrohalogenation just involves two steps. Your first step would be to go and then protonate your double bonds by using your acid, right? So you know you have an acidic proton over on HBr. You go and then break that sigma bond, and you're going to kick off that bromide. Cool. So I forget, where am I going to form my carbocation? Am I going to form it on the secondary or the tertiary position?
tertiary.
Tertiary.
Tertiary position, very good, because it's more stable due to hyperconjugation. Excellent. Now I want to go and then take that remaining bromide and attack my carbocation in order to give me my final product. Okay, so looking at this reaction, first exam-like question I'm going to ask you is, how many stereoisomers?
Two.
Two. Why are we getting two?
There's one, you're forming one new chiral center.
Yep, so you're only forming one new stereocenter, that being over here, right? What if I ran this exact same reaction, but instead of using HBr, I used DBr?
4.
Right, I would get a total of 4 stereoisomers. And why does DBr magically give me 4 stereocenters instead of 2? Sorry, 4 isomers instead of 2.
Because it's different from the hydrogen. It's the heavy hydrogen.
Very good. So the main reason why you would be seeing deuterium in a reaction is because Dr. Falzone is trying to get deuterium to form another chiral center. okay, or just another stereocenter in general. You see here that now we not only have the stereocenter that we have down here, but we also have this stereocenter up here. Why? Because now we have the ethyl group, that propyl group with the bromine and the methyl group, the deuterium and the hydrogen. Cool. So because we have two stereocenters here, we would say we have 2 to the n, and then in this case, our n would equal 4. Cool. Same exact thing would apply with hydration. All right, let's do hydration, and then I'll give you guys a more exam type problem. Okay, so for hydration, remember hydrate or dihydrate. What we're going to do is to first use our acid catalyst, right? Now, having an acid catalyst in this reaction is extremely, extremely important, okay? Water on its own is not that acidic. It actually has a pKa of about 15.7-ish, okay? In fact, organic chemists and inorganic chemists, they have different definitions for the pKa of water, but you don't talk about that. Just focus on whatever you're given, okay? But anyway, sulfuric acid, you're going to need that to actually protonate your double bond, because otherwise, if you don't use an acid catalyst, the reaction will quite literally probably take like thousands or millions of years to happen. Form your carbocation once again. And then now is when you want to come in and then add in your water. Now, I always like emphasizing this because of the fact that people tend to forget this when they actually take their exam, right? Water is neutral, but it's also going to be your nucleophile, right? When you take a lone pair from water and attack here, you're giving that oxygen an extra bond. Oxygen is going to have 3 things bound to it, so now it's going to have a positive charge. Cool, so like that. I always like stressing that particular step because people always forget this. Cool. And remember, the 2 things you shouldn't forget are A, that the extra proton is still there, and B, please, for the life of me, formal charge, okay? Formal charge is the easiest way to lose points on this exam if you're not paying attention to it, so please be careful. Cool. Well, easiest if you studied. If you didn't study, then I guess just like lack of practice would be the easiest, but whatever. That shouldn't apply to any of you guys, okay? So now your next step, you have 2 options to go and then deprotonate. And honestly, you can use either one. Cool. Dr. Falzone tends to use water because water is a lot more present in solution than sulfuric acid is, right? If we're thinking about a safe concentration of sulfuric acid to use for this type of reaction, we're probably using it in about 10% sulfuric acid in water, right? If you have 90% water, then it's a much greater chance that a water molecule is going to react rather than a sulfuric acid conjugate base molecule. Although if you use a conjugate base of sulfuric acid, you will not get that, so don't worry about that. Cool, so you go and then you end up with this product, and essentially the overall reaction was exactly the same as the HBr one, except you are adding an alcohol rather than a bromide. So the stereoisomer situation would be exactly the same. Cool. Let's talk a little bit about our stereochem. Cool. So I showed you guys a bit of a more simple example, but now let's go and then take a look at a more complex example that you might see on an exam. So let's say I have all right, so let's say I have a compound like this and I want to go and then react it with excess HBr. To produce some sort of a final product. Cool. Well, the first thing I would want to go ahead and do is to actually go and draw out my product. Okay. If I'm using excess, that means that all double bonds in the reaction are going to react. Cool. So we know that in terms of where our regional chem is going to be, we're going to have, we're going to have a bromine adding over here. We have a bromine adding over here and a bromine adding over here. Cool. Again, entirely based off of carbocation stability. And we end up getting a product that looks like this. So hopefully that was a product, that's a product that you agree with. Cool. If not, make sure you guys are checking your carbocation stability. All right, so that's the first part of the question. The next part of the question would be how many stereoisomers form? Cool. Now, let's be very clear. When we're talking about the number of stereoisomers that form, we're not talking about the number of overall chiral centers in the molecule. We're only looking at the new chiral centers in the molecule. Cool. So like hypothetically, I guess let's say to make this problem a little more understandable, let me go and then make like this guy wedged, and let's make this guy wedged as well. Cool. So usually in a problem like this, you would have already had some sort of defined stereochem. Okay. So if you have something that looks like this, and I know that this guy technically looks a little incorrect because you shouldn't have 3 bonds in the same plane, but we're not concerned about the stereochem of our bromide right now. We're just concerned about the number of stereoisomers that we form. Well, you see that we would have had so we have, in terms of our new chiral centers, we only have 1 new chiral center over here, right? However, this is also going to exhibit some stereochem here. Cool, because it's also another chiral center. So now let's go and see exactly how many final products we're going to have. Okay, so when we go and then look at this, we see that we have formed 2 new chiral centers. We're going to have a total of 2 to the n chiral centers, which in this case is 2 squared. That's going to equal 4 stereoisomers. Cool. So that's not too terribly complicated. Let's make a bit of a more tricky example, I guess. So what if I took this exact compound I remove this part entirely, and let's have this here. Cool, excess HBr. We know that our bromide is going to add over here and over here. And we get our bromine adding in the other tertiary position as well. Now, my next question for you guys is how many stereoisomers form here? First, how many new stereocenters do we form?
Just 1.
Right, so we form 1 new chiral center, right, over here. However, there is a slight caveat here. Does anyone recognize that slight caveat?
Cis-trans.
Cis-trans, excellent. So this guy right here, although it is not a chiral center, it still counts. It still counts for stereochem because you can essentially have cis and trans possibilities about a ring. Cool. So because we have cis and trans possibilities about a ring, we also factor that into our 2 to the n. Cool. So we technically have 2 stereo. We technically have 2 stereo centers, not 2 chiral centers, but 2 centers where we have some sort of stereochem in there. Cool. So that's it for stereochem for this particular type of compound. Let's do another exercise real quick. Let me add a page here. Let me take this compound. Sorry, that's spoiling the next part. Go away. Okay, that's not supposed to be there. Come on, all the other writing go away. Okay, there we go. Come on, almost there. You're doing great. Go. There we go. I just have to scroll down. All right, so my next question is, if I were to use one equivalent of HBr, where would my first equivalent of HBr add? Cool. So this is where we want to start looking at carbocation stability. All right. So when we're looking at reactivity of double bonds, cool. That's with a carbocation, not C plus. Okay. Then what we want to go and look at is first going to look at where your most stable carbocation can form. All right, so looking at our three double bonds that we have here, we see that this double bond over here can form a tertiary carbocation. This double bond here can also form a tertiary carbocation. And then this double bond in the bottom forms a secondary carbocation. Cool. Right off the bat, we can look at this and say, okay, our secondary carbocation, that's a less stable carbocation, and it'll take a lot greater energy to form that. So because of that, we say that this carbocation is your least likely to form. Hence, this double bond is the least reactive. Okay, then we have our two tertiaries, and our two tertiaries, if we see that there's a tie, the next thing we want to go and look at is the number of substituents. And the rule for that is more substituents is less reactive. Okay, so yeah, we see that between our two tertiaries, we have one that's tri-substituted, that has three substituents. The other one has two substituents. Cool. So the one that has two substituents will be more reactive than the one that has three substituents. Okay. Remember, the rule is that a more substituted double bond is more stable, and if it's more stable, it's less reactive. So that means that one equivalent of HBr would add bromine to that double bond. Cool. So we see that this double bond is most reactive. Okay, and then that other one is kind of like in the middle. Okay, so if I were to, let's say, take this compound and continue reacting, so if I were to do one equivalent of HBr again, then, well, we know that my next most reactive double bond will have to be the other tertiary. And then if I were to go and then take it all the way to the max, get one last equivalent of HBr. And the last one to react will be that one on the bottom. In fact, technically for that last one, you don't even have to write one equivalent because there's only one possible place to add. So then you would end up getting this final product. Cool. So this is why understanding double bond reactivity is super, super important. Now, this is all going to change when we start talking about reactions that do not undergo carbocation mechanisms. Cool. Not too terribly different. In fact, it just starts with a tiebreaker, but you will see when we actually do an example. And FYI, just to continue on with this, if there was a tie for this, look for whether the double bond is E versus Z. Cool. And then you'll realize that the Z double bonds will be more reactive than your E's. Cool. Nice and easy. Ha ha ha. Very funny one. Okay, yeah, let's go and with this, start talking about our next little class of reactions, which is going to be our reactions that involve bromonium ions. Cool. Any questions on anything I've spoken about so far?
Why is the left double bond more substituted than the right one?
Because you see that double bond has two methyl groups on it, right?
Right.
Yeah, or two carbons on it, whereas the one on the right has 1, 2, 3. Okay, so notice that this one on the left has 2 hydrogens and this one on the right only has 1. So that means,
right.
Yeah,
So it's the bond itself, not the individual carbon that we're talking about here. Okay, thank you.
Okay, let's go and then look at our bromonium ion type.
Wait, Juan, sorry, just 1 second. Could you go back to that one?
Yeah.
Why are we not counting the, okay, maybe I'm just not reading it right, but why are we not counting like that third substituent, the dash? Like, why is that not a substituent, but like on the right carbon, all 3 of them are considered substituents, all 3 of the things it's bonded to?
So we're looking at the atoms that are directly bound to the carbon, or like directly bound to the double bond, right? We're not looking anything further past that. So you know that because this bond has 1 hydrogen and this one has 2, then the double bond that has 1 hydrogen is said to have 3 substituents, right? It's only that.
Oh, so we're not looking at the tertiary carbocation for this one? Like,
we're looking at the carbocations, but when we're talking about substituents, we're looking at the number of things that are directly bound to that carbocation, or the number of things directly bound to the double bonds.
yeah,
Cool. That makes
Okay.
sense?
that makes sense. Thank you.
Are we talking about hydrogen bonded to it or the number of carbons bonded to it?
So, I mean, I'm just showing that the number of hydrogens that are bound to it is the opposite of the number of other atoms that are bound to it, right? So if I have 1 hydrogen, that means I have 3 substituents. If I have 2 hydrogens, 2 substituents. When we say substituent, it's basically substituting a hydrogen with something else.
Do you mind just pointing out where the 3 substituents are on the right and where the 2 are on the left?
Here are the 2 here. Here are the 2 over here, and then here are the 3 for this one. Right, we're only looking at the atom that it's bound to. Let me do a different color. 1, 2, 3. Okay, because we know that these green ones over here are directly bound to the double bond. For this double bond right here, and then these yellow ones are directly bound to this double bond. The rest are just hydrogens that are not drawn out.
So are we not looking at what's bonded to the carbon, but rather what's bonded?
Sorry, your volume's kind of low. Can you repeat that?
Oh, okay. So for looking for substituents, are we looking at what's bonded to the double bond, not what's bonded to the carbon?
Sorry, do you mind typing your question in the chat? I can't.
Yeah,
Really?
I'm sorry.
It's okay. So look at the substituents. Are we looking at what is bonded to the double bond, not the carbon? Yeah, that's right. So we're just looking at what's directly bound to the double bond. All right, let's go ahead and move on to the bromonium ion mechanisms. Remember, if you have any other further questions on this, you can ask our wonderful leaders in the chat, or you can ask at the end. Okay, so our next one is going to be our bromonium ion mechanisms. So these mechanisms are your only purely anti-addition mechanisms that you guys have learned so far. The reason why we're observing only anti-addition is because we have a hindered intermediate. In terms of double bond reactivity, we're no longer looking at carbocation stability. We're only looking at the number of substituents and the stereochem. So pretty much like the last two contenders for our icebreaker, for our tiebreaker over here. My bad. I've been a pilot leader for too long. Okay. Next is going to be our looking at our regiochemistry. So our regiochemistry is going to be based off of the stability of the transition state or the stability of your partial positive. Okay. And then your number of stereoisomers will be given by 2 to the n, but the n is different this time. The n is going to refer to the number of double bonds where you went and initiated your stereochem. Cool. I'll talk a little bit about that difference in verbiage in a little bit, but notice that these are quite different mechanisms compared to the simple carbocation reactions. Okay. So in terms of what I mean by this is only anti-addition, if I got my nucleophile and I tried adding it to the top over here, if I tried adding it up here, then what happens is that you're going to be facing a lot of repulsion from that bromide, right? Because that bromide is simply too large and it's also pretty negatively charged. So negative and negative, you're going to have, or negative and electronegative, you're going to have some steric and electronic repulsion there, right? Likewise, if you go on the other side, you notice that there's nothing really holding you back. You can go and then attack from the bottom perfectly fine. But from the top, you're going to have lots and lots of strain from that. Okay. So now in terms of where you add your nucleophile, first of all, please, for the life of me, do not do this. Okay. Bromine, it has a positive charge. That does not mean that it has an empty p orbital, right? That bromine is still sp3 hybridized. If you go in and you add a nucleophile to where the bromine is, you're going to be breaking the octet rule. And we're not doing that here. So what we're going to be doing instead is we have to go in and analyze where we can break the bromonium ion via one of these carbons. Okay, so there we have 2 partial positives. The reason why we have partial positives there is because of the fact that bromine really wants to go and then get its electron density back. Okay, the only way that you could possibly do that is by going and then breaking via one of those carbons. Right, so little bit of a rare case where you have lots and lots of positive charge concentrated in one place, but it's with good reason, right? Bromine hates having a positive charge. It'll go and you're going to have to go and then relieve that somehow. So in terms of where you might want to go and attack, you need to go in and consider the fact that the partial positive on the right is tertiary, the one on the left is secondary. Okay, and if there's one thing you guys should remember, it's that partial positive stability mirrors carbocation stability. Okay. Now, when we're looking at stability here, we're not talking about the stability of the partial positive itself, but we're looking at the stability of the transition state. Cool. So it's going to cost you some sort of energy to do each step of this reaction. It just so happens that it's going to cost you way less energy to go through the more hyperconjugative site rather than the least hyperconjugative site. That is the one that has more substituents rather than the least. So because of that, we would be attacking right over here, cool, at the more substituted side. So now that we know that, let's see how this goes and plays into our mechanism. And this mechanism, quite unique. So what happens is that first we're going to go and then we're going to take the double bond and attack the bromide. Now this is going to be some rather weird chemistry. You see that this goes and then attacks the bromide, and two things are going to happen. First, you're going to break that sigma bond between the bromine and the bromine, but at the same time, the bromine is so large that the one that you're attacking is so large that you're actually going to want to go and donate electron density into that partial positive spot in your on like where your double bond initially was. Don't quite understand that, then whatever, just do it. But just know that this has to happen. You don't get a carbocation here. All right, so now you get that. And then remember, as I drew above, we have to go and then break out the tertiary and not the secondary spot, because that is going to be your more stable transition state. From there, we can go ahead and then attack. We attack here, break this bond. And we go and then we end up getting our two bromides where our double bond used to be. Cool. And now I'm seeing that the bromide is, okay, there it is, there now. So yeah, you see that it's going to be adding there. Okay, so that's just your generic VR2 mechanism. But something that you can actually do is you can do the same exact reaction, but not using bromide as your second step. So we can use a compound called NBS. And we're going to use that to generate low concentrations of VR2. Okay, don't need to know the mechanism how, just know that that undergoes a specific reaction to go and then generate VR2. And I'll show you why you might want a low concentration of VR2. So in doing this, we're going to be changing the mechanism. Okay, and that mechanism is going to change such that the second step is going to involve addition of a different nucleophile that's not a bromide. Okay, if you have too much VR2 in there, then that second bromide actually has a pretty equal chance of attacking as the other nucleophile does. So doing this, is going to give you a compound where you're going to be adding in your nucleophile to the more hindered side for the exact same reasons that we broke the bromonium ion in the more hindered side last time. Okay, this particular one is called a bromohydrin. There are some other derivatives of this as well. We can go and then maybe add in some sort of an alcohol. So I'll make R, I'll write in R here for some generic alcohol group. And then in doing that, we're going to end up with an ether. Also, I don't know why that R left there. Well, exact same mechanism. You just have to deprotonate that one hydrogen that there is there, similar to how you would with water earlier. You can also go and then add in some sort of a different halide by means of a halide salt. So let's say I wanted to go in and I wanted to add in chloride. Then I can use an ionic species like potassium chloride or sodium chloride in order to go and then break my bromonium ion, as you see here. Cool. And the nice thing is that these undergo the exact same mechanisms except with slight modifications. Like remember, for water, you would have to go and then deprotonate similar to how we did earlier. Cool, but I don't need to redraw the mechanism for that. So this is your bromonium ion mechanism. Now let's go back and revisit some of the examples that we did earlier. All right, so let's just grab this from up here real quick. All right, let me stop, or let me erase all of my little annotations here. So let's say that now instead of using excess HBR, we're using excess BR2. Okay, so now we know that we're gonna have to go and then add our bromides in across these double bonds that you see over here. And our final products will look something like this. Cool. So notice that here our bromides went and then added in across this double bond, and this double bond. All right. Remember what I said about stereochem for reactions that are only syn or only anti. Okay, we can use to the n, but just remember that n is going to represent the number of double bonds where we eventually went and created at least one new chiral center from that double bond. Okay, so look at the little yellow highlighted areas that I have over here. That used to be part of the double bonds. So I'll start off with this one over here. Okay, when you look at that one over there, you actually see that we have generated 2 new chiral centers. So that means that this double bond did indeed generate some sort of stereochem, right? But this is basically yes and no, not how many. Did we generate a new chiral center from that double bond? If so, then yes, that will count towards your stereoisomers. Next one, we see that over here, we got 1 new chiral center, being this guy over here. That is supposed to, there you go, highlighted in green. Cool. So because of that, yep, we count that towards our 2 to the n count. Well, we had that over here earlier. And then for this one over here, we do also have 1 new chiral center, but just 1. Whether it's 1 or 2, that still counts towards our count. So that means that we had all 3 of our double bonds going and then forming new stereoisomers. So we would go and then 2 to the n, where n is the number of double bonds that we had to form stereochem. Here it was 3. That's 2 to the 3rd. We have a total of 8 stereoisomers for this. Okay. Let me do a little counter. Let me not use this exact one then, because why don't we try doing this? Okay, here, let's do this.
How do we know that there are no cis-trans possibilities there?
So remember cis and trans possibilities, that would be if you don't have a chiral center, but you still have, what's it called? You still have substituents on the opposite ends of the ring, right? So in the case, to be totally honest, you're always gonna have cis and trans possibilities. It's just that whenever you don't have a chiral center, then you manually have to go and then consider that, like rather than actually putting it in for like the 2 to the n rule, right? I mean, you technically can if you do it correctly, but if you don't, yeah, as long as like you don't have like 2 things on totally opposite ends of the ring, then you don't have to worry about cis or trans. Cool. So let's try this and maybe add in. Yeah, we're fine. So for this one, if I were to go in and add in my BR2, it doesn't have to be excess this time because there's only 1 double bond. Okay, now notice that here we're not generating any new chiral centers, right? You see that here there's only 1 place where you actually go and, where you add in your bromides, but neither of them are chiral centers because you have 2 ethyl groups, okay? Ethyl group here, and then ethyl group here, ethyl group here. So then you have 0 double bonds where you generated new stereochem, so that'll be 2 to the 0. That is just 1 stereoisomer. Okay, so yeah, just remember, if it contributes to stereochem, count it. If it doesn't contribute to stereochem, don't count it. Cool. Now let's go and then look at our double bond Yeah, let's go ahead and then look at double bond reactivity for this. Okay. Use this example again. So when we're looking at double bond reactivity for non-carbocation mechanisms, sorry. All you have to do is take these last two steps over here. So just ignore this little, if there's a tie. So your main thing is to look at the number of substituents, right? And then if there is a tie, then look at E versus Z. All right, so now we want to go and then look at the number of substituents on each of our double bonds here for this compound. So we see that for this guy over here, start off with this guy. Well, we established that that has 3 substituents, right? There's only 1 hydrogen. So that means that everything else that's not a hydrogen that's directly bound to it is a substituent. This double bond has 1 substituent. So because of that, you have 1 substituent, 3 hydrogens. And then for this one, you have 2 substituents. Cool. So if you have more substituents, you're going to be less reactive. So if I were to just go and then add in 1 equivalent of Br2, then now instead of going and then reacting number 2 as, or the disubstituted one as we did earlier, we're going to go and then react the monosubstituted one. That's the most reactive double bonds because we're not forming a carbocation here. So that's where we add first. Our second addition would be to the disubstituted one. So like this. And then our last addition would be to the trisubstituted one. Again, I don't have to write 1 equivalent here because there's only 1 double bond left. But we would go and end up adding to the double bond that you see over here. Cool. So again, two different types of patterns. Make sure that you guys understand the mechanism, because if you do not understand the mechanism, you're going to get this question wrong, unless you guess properly. But yeah, don't try and compartmentalize stuff, because ultimately things all come together in all different places. All right. Any questions about this before I move on to syn additions?
Could you give a quick example of E versus Z?
E versus Z stereochem?
Yeah, of
Oh,
that
yeah,
being
sure,
the
sure.
decider.
So let's say I had a compound like this. Well, you see that I have Z over here and E over here. Z would be the more reactive one of the two, so you would go and react first. Then again, your second equivalent would just come in and add here.
Okay, thank you very much.
Cool. So now that you ask, how many stereoisomers will we observe here?
Four.
So
Oh,
That's a-
actually, you're right. Just two, right?
so this one, let's see. This one, actually, yeah, I made this one a little more complicated unintentionally, but I think this one would actually have some meso possibilities. Cool. So this one would probably be, okay, you probably wouldn't be you probably wouldn't be asked a problem that's like this, like complicated on an exam. So it's like it wouldn't actually be 4. I think like in this case, since we have multiple meso possibilities, it would actually be less. So yeah, I guess just disregard that one. But meso with 4 chiral sensors, that's going to be pretty complicated to find out. Cool. Maybe you guys can go and actually try it out on your own. But if you can't figure it out, then don't stress. I personally would take quite a bit of time doing this myself. Cool. Molly just popped up at the top of the screen. Why'd you get pinned, Molly?
I'm so sorry.
All right, cool. This totally says ammonium ion mechanisms, but I just meant this to be SYN mechanisms. Cool. And SYN mechanisms are going to be significantly different, or like not significantly different, I'd say, but they're different based off of the type of reaction, right? So I didn't have like a general example here, but we're gonna go and then walk through some of the mechanisms that you see here. Okay, so SYN addition, the reason why we observe SYN addition is because we are doing some simultaneous addition across your double bonds. In addition, your double bond reactivity is going to be based off of your substituents in your stereochem once again. Regiochem is going to vary based off of the reaction, and then stereoisomers, the same exact way that we had for anti. Okay, so I'm going to start off by talking about catalytic hydrogenation. Okay, catalytic hydrogenation, we could just go and then take our double bond. If we take a double bond and then react it with H2PDC, we're going to go and then end up with a single bond where that double bond used to be. Cool. It's just the virtue of adding hydrogens across both ends of that. Cool. This is SYN addition only because of the fact that you're adding both of your hydrogens across the catalytic surface. It's not a mechanism you have to know because it involves radicals, so I'm not going to draw it out, but just know that it is SYN addition only. What I am going to do is a bit of an example. Where instead of adding H2PDC, I'm going to add D2PDC. Okay, so you know that if I add D2PDC, I'm going to go in and add my deuteriums across where that double bond used to be. Okay, so yeah, knowing that we form 2 chiral centers, so there's obviously 4 stereoisomers, right?
Wrong,
Why am I wrong, Daniel?
because it's SYN only.
Very good. So SYN only. So remember, it'll just be 2 to the n, where n is the number of double bonds where you initiated stereochem. You only have 1. So you have 2 total stereoisomers. Awesome. So that's catalytic hydrogenation. Nice little breather compared to what we had earlier. Next one, get ready. This is our big boss. This is going to be hydroboration oxidation. All right, hydroboration oxidation is kind of whack because it is a very, very, very long mechanism. but nonetheless, still gotta know it. So I will give you guys a bit of a silver lining. If Dr. Falzone asks you guys to draw this mechanism on an exam, he won't ask you to draw the whole mechanism, he'll ask you to draw part of it. The non-silver lining part of it is that he didn't, he won't tell you what part of the mechanism he'll ask you to draw, like beforehand. So you just have to know the whole thing. Cool. So yeah, sorry for that, but that's what I exist for sometimes, to get your hopes up and then bring them right down. Okay, so we go and then we say that we're going to be adding this quote unquote anti-Markovnikov. Okay, to add in our group where the least substituted side. We are, my internet connection is unstable. Come on, hydroxyl group up here. Let me put my phone on do not disturb. I'm getting a lot of leaders texting me. Okay, so yeah, you're gonna go and then you're gonna get that on your on that least substituted carbon. All right, so I'm going to work out the mechanism with a much more simple example just for everybody's sanity. And I'm just going to work it out with an example that looks like this. Also, make sure you guys number this. Numbering means that they occur in two separate steps. And if you don't number them, you're implying that everything here is in solution, which if everything in there is in solution, then you will get no reaction. Cool, so I will be working with that example for the mechanism. Okay, so this is not rocket science. The first step of your hydroboration oxidation mechanism is called hydroboration. Okay, and with your hydroboration, cool, thank you. Hydroboration, you're just going and then you're gonna be converting your starting compound. Again, this is just only after you've added BH3 and CHF into your trialkylated boron structure that you see here. Okay, so first boron will come in and then, or your double bond comes in and adds to boron. This comes down here. And then we're gonna end up with this first intermediate. And we're gonna do the exact same thing 2 more times. You're assuming you have excess starting material. And we're going to go and then end up with this dialkylated intermediate and then do the exact same thing a whopping 1 more time. All right. Cool. I've gone more in depth into like why we observe the regiochemistry in Learning Done, but Learning Done was when you guys were learning. So you either heard it from me in Learning Done or you heard it from the textbook when you were studying, but I don't have time to go super in depth into this again. Okay, the next part is going to be your oxidation, surprise, surprise, where you just go and then oxidize that trialkylated intermediate. Okay, so yeah, we're going to be doing quite a bit of stuff with this trialkylated intermediate. But before we do that, guess what? We got to do something else. We're actually going to take our hydrogen peroxide, react it with our hydroxide that we have in solution, and we're going to form a peroxyanion and water. Both of these are going to be involved in another part of the mechanism at some point. Okay, let me actually go in and just start this on a new page. So we're going to take our trialkylated intermediate. We're going to add this guy in. okay, our peroxyanion. Remember, boron has an empty p orbital, so that empty p orbital is going to go and then accept that. Then we end up with this intermediate, but oh my God, this intermediate will not get me full points on an exam. Why will this intermediate not get me full points on an exam?
Formal charge
Yep, formal charge on what?
on the boron.
Boron, right. Boron has 3 valence electrons. So having a negative charge on there, you now have 4 valence electrons. Very good. Now you're going to do a next step, which is actually a 1,2 alkyl shift. And that 1,2 alkyl shift just involves shifting this alkyl group over to this oxygen. Now, what do you notice here that's going to drive this step? What characteristic of that intermediate drives that step to completion?
Weak oxygen-oxygen bonds.
Yep, the oxygen-oxygen bond is extremely weak. So because whenever you see an oxygen-oxygen bond, just assume that you're going to be breaking it very, very soon, which in this case it's right now. So you go and do that. And you're going to end with this intermediate. Again, that was after 1,2 alkyl shift. And there we go. Yeah. So unfortunately, this mechanism is kind of a pain to draw. So I'm going to save myself the pain of drawing it and copy and paste this, but you guys can't do that on your exam. So that's the muscle memory of this reaction. I'm feeling quite sassy today. I don't know why. Okay, so then you end up with that intermediate first. This guy now has an oxyalkylation. And you would go and then do that exact same thing a second time. And guess what? You will go and then, oh, sorry, one thing I should add though, this is not, the oxyalkylation one is not the one that moves. Cool. And then you go and then do your little alkyl shift to go and then end up with your second intermediate. And yep, we do it once again in order to end up with our fully alkoxylated intermediate. All right, so then we go and then do another 1,2 alkyl shift, and our final product just has 3 boron oxygen bonds, right? And then each of these steps, we are generating hydroxide as a byproduct, which that hydroxide becomes important very, very soon. Cool. So that's another step that happens 3 times, and then we're going to do yet another step that happens 3 times. Okay, this time we're going to go and then add in our hydroxide into our boron with an empty p orbital. Okay, I'll zoom out afterwards so you guys can have time to copy things down if you didn't get the time. So the hydroxide will come in and then attack the boron over here. Okay, you get this intermediate once again. Please do not forget formal charge. And then afterwards, you're going to go and then kick off one of your alkoxy groups, right? In order to end up with this final product or this final intermediate. Now, notice that you do have to go through that intermediate because that boron is sp2, and you can't just freely kick something off, especially since boron's LUMO is an empty p orbital. So you're going to have to go and then put your electrons into that empty p orbital before anything else can happen. And like everything else in the mechanism, we do this 2 more times. Okay, and also I should note that every time you're doing this, you're ending up with this oxyanion. Okay, and you're gonna do this one more time. So this. And you end up with this intermediate and then the oxyanion that you see there. Okay, now after you go and then generate that oxyanion, you're gonna have to do one last step. Probably the easiest step in the whole mechanism, where you just go and then add in water. And we are working in basic solution, so whenever we're working in basic solution, water will be a little more acidic, i.e. it's the most acidic thing we have in solution right now. We grab this proton, and then we end up generating our final major product plus water. Okay, and then I should also note that there are 3 of these in solution. Okay, I mean 3 equivalents of it rather, not exactly 3 molecules, that would be absurd. Cool, so that is the second step of your hydroboration oxidation mechanism. I know I kind of went fast with this, so I'll give you guys maybe about like a little less than a minute to copy down whatever you didn't. Meanwhile, I'll take a quick breather.
Juan, wouldn't you get 3 OH minuses?
Sorry?
At the end? At the end.
Oh yeah, OH, yeah, not water, maybe.
Is it 3 OH minus or OH?
What was that?
Is it 3 OH minus or just 1?
Yeah, it'll be 3. I mean, just like 3 of like everything pretty much.
Okay.
Yeah.
Then we also end up with a BOH3.
Sorry, I still can't hear you that well.
Oh, okay, it's okay. I'll just have it.
Yeah, after you send your if you send a message in the chat after that, I'll keep going. Okay. Yeah, so your other byproduct will be your BOH3, which like you see over here. So this will be a byproduct. This is your major product. All right. So let's go ahead and keep going. Next one I'm going to do is a bit of a breather, which is your epoxidation. So in order to do epoxidation, you are going to need a couple things. You will need something called a peracid or peroxyacid, which looks like this. And as the name implies, you will be forming an epoxide. Epoxide is a 3-membered ring that contains an ether, which looks like this. Okay, so now we want to go ahead and then draw the mechanism. In my opinion, this is probably my favorite mechanism to draw. It's just a bunch of like, swirly arrows all over the place. So what I'm going to do is that I'm going to overlay my peroxy acid above this, as you see here, or it could be below. We could form two different stereoisomers here. But essentially, what we're going to do is that we're going to take the electrons from our pi bonds. We're going to add it to our oxygen, break our oxygen-oxygen bond to form a carbon-oxygen double bond. Take your electrons over here to grab a hydrogen, and then break that hydrogen-oxygen bond in order to go and then bring your electrons right back down. Okay. In doing that, you'll end up with this final product. Cool. And then you can also go and then do the exact same thing from the other side as well, if you want to see how the other stereoisomer is formed. Attack, break weak oxygen-oxygen bond, grab hydrogen, then bring this down. Then we end up with this final epoxide product that you see over here. Cool. So epoxidation, short and sweet, not too bad. This will actually be number 3 in these types. Okay. Our last SYN mechanism, and then ozonolysis. So our last SYN mechanism is going to be osmium tetroxide, which I've seen a lot of people still somehow haven't recognized this reaction. So this is going to be your dihydroxylation. Okay, another 2-step mechanism. And then you're going to go and then end up with alcohols on either side of where your double bond used to be. Okay. Please write. My screen has been doing so well. Please don't freeze now. There we go. All right, yeah. So our dihydroxylation mechanism, 2 steps. First is going to be the addition of your osmium tetroxide to form your osmate ester. Okay, osmium tetroxide, it looks like this. And then what's going to happen is that we're going to go and then we're going to take our electrons from here, attack this oxygen first. I'm going to bring some electrons into osmium, and then this pi bond will come right down here. Cool. You end up with this intermediate. Which is called your osmate ester. Okay. Now, the next step will involve breaking this osmate ester to go and then form your new alcohols. Okay, so first of all, you're going to go and then take your sodium sulfite, or NaHSO3. And you're going to react it with water. In order to go and then form this conjugate acid. Plus a hydroxide. Okay. Now we're going to take the hydroxide and then add it back into our osmate ester. So the hydroxide comes in and attacks the osmium over here, breaking this osmium oxygen bond or coordination, whatever you want to call it. Then you get the oxyanion that you see over here. Then take your other hydroxide and then do the exact same thing. Yeah, I missed the oxygen over here. My bad. Cool. There we go. Much better. So we oh man, there you go. So now we go and then attack in once again. Then we end up with this dianionic species over here, which you can go ahead and then just quench by using that by using that conjugate acid that you formed over here. Okay, so then go and then grab this, deprotonate here. Then you do the exact same thing again in order to end up with your final product. Cool, and that is your dihydroxylation. Cool, bit of a unique mechanism, involves a lot of like work with your metal there, but still it's still a pretty decent reaction to work with nonetheless. Okay, because you have two alcohols on opposite sides of your double bond. Okay, any questions on number 4 or any of the reactions, any of the syn reactions I went over before I go on to the ozonolysis?
Yeah, does it matter which oxygen breaks off of the OS first?
Doesn't matter.
Okay, cool.
The substituency of the left carbon doesn't affect it.
Not necessarily. I mean, it's like a very, very like subtle difference, and you guys aren't really responsible for like the differences for that anyway. All right. So little bit of a spoiler alert. Ozonolysis is one of Dr. Falzone's favorite reactions of all time. If you take Orgo 2 with Falzone, you will not see the end of it, which is also why it's a great idea to take Orgo 2 with Falzone if you took Orgo 1 with him. Okay, so yeah, ozonolysis. The overall reaction for ozonolysis will look a little something like this. So let me use some sort of a generic compound over here. So your reagents for ozonolysis are going to be, first step will always stay the same. Ozone at -78 degrees Celsius. Second step will be zinc and water. But another possibility that you can see here is what's it called? DMS, dimethyl sulfide. And acid. Cool. You could see either one of these examples on an exam. I personally have actually ran this reaction with dimethyl sulfide as a workup. Spoiler alert, dimethyl sulfide smells really, really, really bad because of the sulfur. Okay, so when you do that, you're essentially going to be going and then cleaving this carbon-carbon bond over here to give you two products containing carbonyl compounds. Okay, and then this something really, really important. This little piece of advice will help you out a lot, especially for riddle problems. One carbon-carbon bond, after cleaving it with ozonolysis, will give you two carbonyls. Okay, so why is that important? That means that ozonolysis will always give you an even number of new carbonyls. So two new carbonyls rather. Cool. So very useful for when you're going and then you're running you're doing one of those riddle problems I said earlier. Now for the mechanism. Mechanism, honestly, it just requires lots and lots of practice because it requires lots of little steps along the way. So let's go and then see how that looks like. For the mechanism, I will use this example, which you guys saw in pilot this week, but it's worth going in detail with this example particularly. All right, so first we want to go ahead and start off with ozone. Ozone, you might see it present in like one of its main resonance structures. So here's one. I'm going to draw in all the lone pairs here. And then another resonance structure that you can see will be with a double bond between these two oxygens. Cool. So choose whichever one you want to start with. I personally like using the one on the left. So I will start by taking my compound and then reacting it with my ozone here. You don't have to draw in the lone pairs unless you specify to draw in the lone pairs. So I would know how they look like anyway. So this comes and attacks down here. This end of the double bond comes up and attacks over here. And then you end up with this little intermediate over here, which if you notice that intermediate has an abundance of oxygen-oxygen bonds. And surprise, that's actually the first thing we're going to do. It's not weak enough to break just spontaneously on its own, but something else can actually go and then drive it to break. And that's going to be that the carbon-carbon bond over here breaks to form a strong carbon-oxygen double bond, breaking this oxygen-oxygen bond that you see over here. Okay, so then you end up with this acetaldehyde that you see over here. And then this other intermediate that has formal charges that are lagging. Okay, come on, we're getting there. Cool, and then you end up going, and then you end up getting those two intermediates. Cool, this thing lags a lot, but trust me, I've actually seen someone take 10 minutes to draw full epoxide. All right, so now, usually when Dr. Falzon shows this, he says to turn over one of the molecules. Turning over is not a mechanistic step. Turning over simply, he just does it to make it easier to see how, to make it easier to see exactly how things align, right? By things, I mean your dipoles. So you know that this carbon will be partial positive, this oxygen will be partial negative. Okay, so yeah, you know positive and negative will align, negative and positive will align. So by this, what's going to happen, it'll actually help if I turn this over. So I'll go and then take this over here. Haven't done anything yet. I'm literally just duplicating and turning things over. Okay, maybe I'll turn this guy towards the other one. Then this negative charge, or the lone pair from that negatively charged oxygen, will come and then attack this carbonyl. These electrons will go and then form a new bond over there. Cool. I used to call this next intermediate something that looks like a car, but someone pointed out that it actually looks more like a penguin, and I wholeheartedly agree. So here's your ozonolysis penguin. And just to lighten up the mood a little bit, I will physically make it into a penguin. And it's actually a penguin holding its hands up saying good luck on your exam. Now, I don't think that will come on up here. Yeah. I don't think that will actually like get you points if you draw it on your exam, but if you want to make a grader laugh, you can always go and then draw out a penguin. Okay. Then afterwards, next up, you either add in your zinc or your dimethyl sulfide, whichever one he gives you. Your zinc will come in, and as expected, you break the weak oxygen-oxygen bond. Okay, and then finally, you can go ahead and then reform your carbon-oxygen double bond. That's going to break this sigma bond, form another carbon-oxygen double bond, and then kick off zinc oxide. And this gives you a final product of 2 acetaldehydes. And a zinc oxide byproduct. All right, cool. So that's your ozonolysis mechanism. Any questions on ozonolysis?
Is it possible that we go through some exam questions on that?
I still have a bunch of stuff to go over, so I've gone over through a few examples already, but I'll go over more examples after I'm done with alkynes.
If you have specific exam questions, feel free to like chat one of us or stick around for the last 30-minute session where we'll like try and talk about those types of things.
Mm-hmm. Okay. So now let's go ahead and talk about alkyne reactions. Cool. Alkyne reactions are a little less exciting than your alkene reactions, but they do still serve a purpose. Okay, so for your alkyne reactions, again, one of them will be your hydrohalogenation with HBr or some other halogen that's not fluorine. Okay, so HBr, one equivalent of it is going to give you a bromide that has added to the more substituted side of that triple bond. Okay, so what's it called? Yeah, it's really important to go in and specify that you have one equivalent over here, because if you don't specify a number of equivalents, that can be a little ambiguous, but usually for organic chemistry, we say that if you don't specify equivalents, that you're assuming excess, and excess means that you would go and then add in too much HBr, or you would add an HBr like all the way. Cool. So you would end up getting something that looks like this. Okay. Next, actually, let me show you guys a reasonable mechanism that he shows. So this is, I guess, like a somewhat reasonable mechanism. However, this is not a 100% accepted mechanism amongst organic chemists. Particularly, I don't like it too much because it's a termolecular reaction, and the likelihood of three molecules reacting at once is pretty unlikely. But essentially, the way that he shows it is that the bromide comes in, then attacks over here, and then this triple bond will go and then essentially attach to that proton on the other side, and then kick off your bromide. Cool. So then you go and then you end up with your final product as you see over here. Okay. Some other examples. For the bromonium ion mechanisms, those are a little tricky. I mean, they still work the exact same, but you might run into some issues like the bromonium ion that forms is quite strained. So don't worry too much about those types of mechanisms. Cool. So taking one equivalent of Br2, we'll go and then give you this product. Notice that I drew the product anti. Usually this will prefer to add anti because, because of things like steric hindrance or electronics or whatnot, but mainly the fact that the molecule that you end up getting is E, which would be more stable than Z. Okay, some other ones. Another one that you might potentially see. Am I missing any other ones? Or at least like in the order that I'm trying to go in. Okay, yeah, we're going in a good order. So this is the one that where you start seeing a bit more exciting stuff. Cool. So water and sulfuric acid, and I'm specifically not putting one equivalent here. You can, but to be honest, you only need one equivalent to get the reaction to occur, right? Because what's actually going to happen is that we're going to go and do the exact same thing we did with our bromide, where we're getting a vinyl alcohol like we see over here. Cool. So is this going to be my final product?
No.
No.
Why not?
It has to tautomerize.
Very good. So this is actually going to go through a process called tautomerization. Where you're going to go and essentially convert this into its keto form that you see over here. Okay, so when I say keto form, we said this is your enol form, and this is your more stable keto form. Okay, tautomerization is why we have a keto diet and not an enol diet. All right, so the way that the mechanism for this particular step works, you'll just need a little bit of water in solution. So all that happens, again, Falzone depicts it as a termolecular mechanism. Is that the water will come in and then grab this proton over here. You're going to form your carbon-oxygen double bond, and then you're going to get another proton over here. Okay. Notice that these two compounds actually are constitutional isomers of each other. Essentially, we're going and we're moving the hydrogens from one to the other. Okay. So, yeah, so we're going to have that. Now, if you wanted to do anti-Markovnikov, so your first instinct might be to use BH3 CHF. And then oxidize that. Well, guess what? This one actually is not really a good choice for alkynes, right? We actually have a better, more beefed up version of BH3 that we can actually use for alkyne reactions instead. Okay, and this can actually be accomplished with something called 9-BBN. And I know how much you guys all have a love-hate relationship with bicycles, but this is a bicyclic compound. And you guys are probably not going to be expected to draw out 9-BBN. However, Dr. Falzone, he might draw it out for you, and you guys should be able to look at it and say, okay, that's 9-BBN. So two different representations that you might see, it might be the planar form. bicyclic 8-membered ring. That's one of them. And then your other form might be, bear with me because this is going to be a bit of an ugly drawing. Like this, which is technically the more correct way of representing it. Okay, so the way that 9BBN is synthesized is just you have the cyclooctadiene. It's a specific type, it's not conjugated, and you're going to go and then form that using a regular BH3 reaction like I showed you guys earlier. So you would want to go and then no, I don't want to convert handwriting into text. So you would want to use 9BBN instead. So you would go and then end up with this enol once again, but remember, you're never ever going to selectively stop at an enol. That enol will go and then tautomerize into the keto form, which in this case, the keto form is an aldehyde. Okay. In addition to this, we also have some pretty good use of 9BBN, considering the fact that 9BBN is very, very hindered. Cool. So let's see how hindered exactly this is going to be. So let's say that now I have an alkyne that's not terminal. Okay, so I have an alkyne that looks like this. Well, if let's see exactly what we can do with the compounds that we have. If I were to go and use water and sulfuric acid, I would still end up with ketones as you would expect. However, I don't particularly have good selectivity for either one. Okay, so water and sulfuric acid is not an ideal choice for this because you have poor selectivity. But if I use 9BBN, what happens is that 9BBN is so hindered that it wants to go to the least hindered side of the alkyne. So you will get the selectivity towards the least hindered carbonyl. Cool. And that's just because of the fact that 9BBN is so big that you wouldn't be able to go in and favor the more hindered one. Now, in terms of favoring the more hindered one, we don't really know any types of reagents that can do that for us just yet. So don't worry about forming the more hindered one. You'd always want to go to the least hindered one. Okay. So now let's go and then we can also see how we can work with 9BBN for double bonds as well. Okay, so here, using water and sulfuric acid or using BH3 would not give you good selectivity, right? Because both sides are secondary. However, 9BBN will give you good selectivity because it wants to go in and place the alcohol in the least hindered site. Cool. So doing that, you see that of these two sides, this one is the least hindered one, right? It's farther away from that 6-membered ring. So we can go and then ends up getting our alcohol at that position. Okay, and then similar to BH3, it's syn addition. So you would only be getting, regardless, you'd only be getting 2 stereoisomers. But remember, you have to use the syn rule for seeing how many stereoisomers you would have. Okay. Now I'm going to go and then talk about, or one last reaction that can tautomerize, I guess. So let's do this. Well, this will be number 5. If I were to use NBS and water, cool. So you would get the exact same regioselectivity as you would expect for an alkene. Sorry. It's weird. Like it's so hot in my room right now because my building turned off the AC, so we just have the heating, which means that now when I'm holding my Apple Pencil, my hand gets really sweaty, so it feels like it's like slipping out. But yeah, now you see this, and then once again you have an enol that would just go and then tautomerize. Into the ketone form. So if you ever wanted to get an alpha bromoketone, this would be a really great way to synthesize it. All right. There's 3 reductions that you can have for alkynes, however. So I'm going to go ahead and quickly talk about those. Okay, so 3 different things that I could do. The first one is going to be the reaction that I've seen before, and that's H2PDC. Now, H2PDC is very strong. Those of you who've talked to me, I've told you guys my story about how I've dealt with H2PDC, and the palladium charcoal catches fire very quickly. So what actually happens there is that H2PDC will reduce to directly to the alkane. Okay. We actually do have 2 other reducing agents that we can use for this stuff. One of them is called H2 and Lindlar's catalyst. Okay, and we say that Lindlar's catalyst is a Poisson's catalyst, okay, meaning that it's somewhat deactivated, and as a result, you're actually going to end up with a cis alkene. Okay, and then for your trans alkene, we actually have a type of reduction called our dissolving metal reduction. That's just with sodium and ammonia at -78 degrees Celsius. Sometimes I have seen lithium used as well. So you can use sodium or lithium, either one is fine. But then this will give you the trans alkene. Okay, so yeah, so this is some really, really great ways to go and actually control the stereochem of your reaction, right? I'm going to segue into some practice with this real quick, but are there any questions before I continue? All right, so let's go and then do some fun practice with this. So let's go and start off by let's say I have this alkene over here, and then I want to end up with this final product. Cool. So it'll be this and its corresponding enantiomer. All right. So looking at this, you notice something really, really weird right off the bat if you've been studying, right? And that really weird thing is that you have your alcohols look like they added anti to each other, right? So are there any reactions that you know that give you alcohols adding anti to each other? Don't say breaking up oxides because you technically don't know that yet, but in case you do, it's not that. So you guys actually, yeah, the silence is, I guess, correct. You don't know any reactions that can go and then give you can give you a trans or can give you an anti-addition of alcohols, right? However, we can do one really cool thing with alkanes, and that is that we can go and then rotate them. So what I'm going to go and I'm just going to go and then rotate this. And guess what? The molecules that I have drawn on the bottom are the exact same as the molecule that I have drawn on the top. Don't believe me? Let me just find absolute configuration for you to prove it. So if I find absolute configuration, I'm going to get that this is going to be 1, 2, 3. This is going to be S. And then this one, 1, 2, 3. This is going to be R. Then this one's going to be R, and then this one's going to be S. Okay? When I go and then find my absolute configurations, you're going to see, or like for the other one, you're going to see that this one, of course, will stay S, this one, of course, will stay R. However, the next one, you see that when I number it, this is going to be 1, 2, 3. I'm going clockwise, that's still going to be R, right? Similar to how up here I had 1, 2, 3. This guy was counterclockwise, but we had to flip it because our lowest priority is in the front. So these are the same exact compounds. Now you see that the compounds on the bottom that I've drawn, they look like they have added syn. So because of that, we actually have to be very careful with the stereochem of our alkene. But we see that if you look at the if you look at the alkane backbone of this, oops, my screen froze. There we go. Yep, if you look at the alkane backbone, you see that this would have added syn onto a cis alkene. Right, so this is another one of the very big things that you have to ponder on when you're solving these types of problems. Okay, whether you add it to a cis or a trans alkene. So when you go and then when you draw your last intermediate, your last intermediate would have had to look like this, right? If you're not entirely sure, go ahead and if you're not entirely sure how this works, go ahead and then put it into the force perspective and see for yourself, right? But you know that your OHs would have to have added over here and over here. You get that, and then of course the OHs can rotate and Falzone can be very tricky. One of my former pilot students very affectionately called this trick the Falzone sneaky because Falzone likes to be sneaky with you guys. So when you look at this, just realize that Falzone pulled a sneaky on you, and you can rotate your alkanes such that you don't rotate alkanes within rings. Okay, so that means that now we know exactly how we got here. So first, you can go and then take this and then reduce to the cis alkene, and we know that we could do that by using H2 Lidlars. Cool. And then your second step, well, you know the reagents to go in and add in your hydroxyl groups. That'll be step 1, OSO4. Step 2, NaHSO3 and water. Cool. So yeah, make sure that you guys are very, very wary of this because double bond or single bonds can certainly rotate and stereochem can be depicted to trick you. Cool. Let's work out another example. Let's say we have wow, my thing totally just disconnected from my iPad. Come on, we're doing so well today. Yeah, for those of you who go to learning, then you guys know how a struggle this is. Come on. Let me see my Wi-Fi settings, see if I'm connected to this Wi-Fi. Looks like we're connected to the same Wi-Fi. I don't.
Do you want to try turning your video off?
Yeah, I guess. Let's see if that works.
While he's doing that, does anyone have any questions? Cool.
Yep, it's not a review session if there are no tech issues. Now it's not able to. All right, I'm gonna log into Zoom through my iPad and screen share through there. It'll take me a few seconds. All right. Fingers crossed. Come on. There we go. All right. Okay, so let's say we have a product that looks like this, and we'll have the respective enantiomer as well. Okay, so we can go ahead and then see how this works. Well, same thing. First, you see that you have two bromines that look like they added syn to each other, but they definitely did not, because you don't know reaction that does that. So we would have to go and then rotate. So then these compounds would actually look something a little more like this. So what you see right here. Okay, so yeah, now we know that when we added our bromides, that means that we needed to add to this backbone over here, which looks like it would have come from a cis alkene. Cool. And then we know how to get from here to here. So when we see that starting from our starting material, we can go and then add in sodium and ammonia at negative 78 degrees Celsius. Remember, that's our dissolving metal reduction to go and then give us transalkene. And then next one would just be Br2, which, adds anti. Cool. So another of your little files is sneaky. So make sure that you guys are very careful with that so Falzone does not sneak you and you get the grade that you want on your exam. Okay, 757. Let's see. Yeah, I think I'm just pretty much about done with review and the examples that I have. There are some more examples that I wanted to do, but you will be seeing a lot of different exam type questions in your pilot sessions this week. So please be sure to attend pilot this week, or else you will make your pilot leader and the rest of us very sad, and maybe your exam score too. So go. All right. If you guys have any more questions, we're going to be hanging around for another 30 minutes for like a little Q&A session. Otherwise, I hope you guys found this helpful. And you are free to go. If you have any feedback, you're welcome to leave it in the chat.
So yeah, on that note, the way that we're going to be handling the Q&A session is we're going to be going into 4 different breakout rooms. So I'll just automatically assign everyone into a room with one of us, and then just feel free to ask any questions. If you don't have any questions, though, just feel free to hop out. And yeah, good luck on your exams.